Good morning. Last time we talked about the Poisson distribution, which was looking at the number of times something would occur in a continuous interval. So for example, what's the probability that 7 cars pass through an intersection within an hour? Today we're going to talk about a waiting time distribution. So for example, what's the probability that it will take less than 3 minutes for the next car to pass through the intersection? So Poisson would ask the question, what's the probability that 4 cars stop at an intersection or pass through an intersection in 1 minute? So now, what we're interested in, what's the probability that we have to wait, let's say less than a minute, for the next car to pass through that intersection. So the difference is that this guy is discrete. We're counting things. And here we're looking at a continuous distribution because we are looking at time, which is a continuous quantity. So a couple of notes then about this. First, as I said, the distribution that we're going to be looking at today is a continuous distribution. Second, theoretically, the waiting time can be between 0 up through some arbitrarily large amount, some large number. So the sample space here is 0 to infinity. So let me also say that if you think about it, this distribution has to be related to this distribution intimately. Because if there are more cars that pass through an intersection per minute on average, then your waiting time for the next car should go down. Those guys are very much related. And in fact, we're going to use the Poisson distribution to derive this new distribution, this waiting time distribution, which is also called an exponential distribution. So let's see how we derive this waiting time distribution using the Poisson distribution. So let's let W be our random variable, and it's the waiting time until the next event. So in this car example, the event would be the cars passing through the intersection. So as I've said, with continuous distributions, what we typically do is we look at the CDF. So the CDF in this case is the probability that we have to wait less than some given amount of time. So this is how I'm going to derive this waiting time distribution. I'm actually not going to look at this guy. I'm going to look at its complement. In other words, I want to study 1 minus the probability that the waiting time is greater than some value W. So 1 minus the probability that I wait more than 2 minutes or wait more than 3 minutes. Now, why do I want to do that? Well, if I want to wait, if I need to wait more than some unit of time, then that tells me that in the interval from 0 until that unit of time, there were no events. And that's something that I can count, so I'm going to be able to use the Poisson distribution. So in other words, this is 1 minus the probability that no events occur in the interval from 0 to W. And this is a definite number. This is probability that there were 0 events in this interval. This is trickier because if I have to wait less than 6 minutes for something to occur, I have no idea how many events occurred. But this is one definite event. So if I can figure out which Poisson distribution, which parameters I need, then I'll pretty much be done. Well, let's think about this. Let's say on average, there are 2 per minute. So lambda is 2 per minute. Well, what would lambda be if I look at the interval from 0 to 2 minutes? Well, hopefully you say, well, that'll just be 4. Well, what if then I'm interested in W minutes? So I'm interested from 0 to W. So pause the video, see if you can come up with the correct lambda. Right, hopefully if you said, well, 2 per minute, 4 per 2 minutes, then I guess it's twice, twice whatever W is for W minutes. So if we then make this abstract and instead I say, oh, it's lambda for 1 minute, whatever the heck lambda is, then for 2 minutes, it's going to be twice lambda. Well, then for W minutes, my correct parameter is lambda times W. Hopefully that makes sense. There's lambda in a given minute on average, then over the interval from 0 to W, there's going to be lambda times that W on average. Okay, so that's what our parameter is. Pause the video, see if you can come up with the correct probability. All right, hopefully you said 1 minus e to the minus lambda, where lambda is lambda times W. Lambda, which is lambda W to the x, well, what's x? We know events, so that's 0, over x factorial, over 0 factorial. Beautiful. Something to the 0 is just 1, that's just 1. So we have derived the CDF for this waiting time distribution. And let me be clear about this. Big F of W, this one's interesting. Let's write it up here. So I guess we have big F of W is 1 minus e to the minus lambda W if W is bigger or equal to 0. And it's going to be 0 if W is less than 0. All right, so that's what our CDF is. Give you a minute, come up with the PDF for this. Right, hopefully you paused the video, you gave it a shot, and you just have to take the derivative of this guy. So we have to use the chain rule from differential calculus. So the derivative of 1 is 0, the derivative of e to stuff is e to stuff times the derivative of that stuff, with the derivative being with respect to W. So the derivative of lambda times W, if W is the variable, is just going to be lambda. But we've got a negative here, so the derivative is going to be negative lambda. Negative lambda times a negative becomes positive. So we have lambda e to the minus lambda W. And again, this is going to be the case if W is bigger or equal to 0. And just so that we can visualize this distribution, this is just an exponentially decreasing function. If W is 0, this evaluates to lambda, and it decreases forever over here. And then it's just 0 on this side. So this would be the graph of the PDF. All right, so let's now tie all that together. This is the PDF of this waiting time distribution, and this is where, again, lambda is the mean number per unit time. So it could be per minute or per hour, whatever you're studying. We usually don't write it like this, but this form is going to be helpful, as we'll see in a couple of minutes. The usual form of this distribution, this waiting time distribution, is as follows. We're going to let theta equal 1 over lambda. So again, lambda is just the number, the mean number per unit time. And if we write it like this, our f of x becomes 1 over theta, because since theta is 1 over lambda, lambda is 1 over theta. e to the minus x over theta if x is bigger or equal to 0. Really, no difference in using x's or w's. This is just standard to write it as an x here, so that we can then write the expected value of x and the variance of x. So why do we do this? Why do we write it like this? Well, if you write it in this form, then when you compute the expected value, you actually get theta. So there's something nice about that, that the expected value of the distribution is the parameter. Analogous to what we saw with the Poisson distribution. The expected value of the Poisson with parameter lambda was lambda. The expected value of this exponential distribution is theta, and it's got a parameter theta. So there's something elegant about that. The variance happens to be theta squared. So I'm not going to work it out, but I would love for you guys to try to derive that. It's very satisfying to get this, and I'd be happy to work this out in discussion if people would like me to do so. So basically, you want to prove that this guy, right, this is the expected value of that distribution, is equal to theta. And this would be a good practice integration problem, especially if you haven't seen integration in a while. There are two nuances about this. One is that this is going to be an integration by parts problem. So I'll even start you. If you let u equal x, dv equal 1 over theta, e to the minus x over theta dx. So that's one piece of the puzzle, integration by parts. Another piece of the puzzle is that this is an improper integral. So if you've forgotten either how to do improper or parts, then you definitely want to review that, because that will pop up. So maybe, let me even call this problem a good self-assessment. If you can work through this problem, you're set. This is as difficult as it gets. If you can't do it, again, that's fine. Just shoot me write something up in the discussion, and I'd be happy to work it out. But you really want to review these concepts. All right, so let's do a couple of examples. Actually, one more thing before I do. Let me point something out. I said at the beginning that the waiting time distribution, which we're also going to call, we should give this a formal name. So x is distributed as an exponential distribution with parameter theta. Again, it does go by the waiting time distribution or the exponential distribution. I said that if the number of, if the mean number of occurrences of an event, that should be related to the waiting time. Well, we see exactly how it's related. As the mean number of times that an event occurs per unit time goes up, we have a 1 over relationship with the mean waiting time for that event. So that's the exact relationship between those two. All right, so let's do some work with this. Let me also say one last thing. This is a lot to memorize. I wouldn't memorize it all. Personally, I would have this guy committed to memory. Feel confident that you can take a derivative. And then remember this relationship. And then you can get this guy here. So why do you even need both? Well, questions might be posed in terms of the mean number. They also might be posed in terms of the waiting time. So depending on what information you're given, it might be more fruitful to think of it in terms of one way or another. Let's do a couple of examples. So let's say the number of customers follows a Poisson process. So that's basically saying that the underlying counting distribution is Poisson. Okay, so this is at a bank, and let's say the bank expects an average of 30 customers per hour. So two questions. First, what's the probability that you have to wait more than 3 minutes? And what's the expected waiting time? So pause the video, give these a shot, try one or both, and then start the video up again. Okay, so I'm interested in what's the probability of waiting. I verbally said, but I didn't write this down, waiting more than 3 minutes. So my unit here is per minute. My unit is per minute. Okay, well, if my unit is per minute, then I need to come up with my lambda. I'm given information as the number per hour. Well, if it's 30 customers per hour, you might be able to just do this in your head, but let me just write out the details. 30 customers per hour. And we've got 1 hour, it's the same thing as 60 minutes. So if you multiply those guys together, we get the customers per minute. So we have 1/2 customer per minute. Okay, so I want the probability of waiting more than 3 minutes. Well, in terms of CDFs, that's just going to be 1 minus big F of 3. Because big F of 3 is the probability of waiting less than or equal to 3 minutes. So this is 1 minus, and this is where it gets a little dicey. F of 3 is another 1 minus, so you have to be careful here. We have 1 minus e to the minus lambda. Lambda is 1/2 times a waiting time of 3 minutes. So we get e to the minus 3/2. So let me say that there are actually 2 other ways that you could have solved this. One way that you could have solved this is you could have also integrated from 3 to infinity, waiting more than 3 minutes. My lambda, which is 1/2 e to the minus 1/2 w dw. So that would have been another option. Or I could have integrated from 0 to 3, e to the minus 1/2 w times 1/2, and take that value, because here I'm just taking 1 minus this guy. I wouldn't do this. I would not do that because I already have the CDF. But I want to point out this because I want you guys to really get that relationship between the PDFs and the CDFs. All right, finally, what's the expected waiting time? Well, you know that lambda is equal to 1/2, and theta is 1 over lambda. So the expected waiting time, or on average, customers should expect to wait for 2 minutes. All right, let's do one more example. Example, the waiting time for the next car to approach a traffic light is given by f of x equals 3e to the minus 3x, where x is in minutes. So x is in minutes. So my question is, what's the probability that there are 2 cars in the next minute? So again, give that a shot, pause the video. Okay, well, let's see. This is a counting question, so it's a Poisson distribution question, so I need to know what lambda is. And lambda, by what I see here, is equal to 3. So 3 cars in the next minute is just going to be e to the minus lambda. 2 cars in the next minute, lambda to the x over x factorial. All right, so today we talked about the exponential or weighting distribution. It is intimately related to the Poisson distribution. The Poisson distribution counts the number of times something occurs in a particular time interval, and the waiting time or exponential distribution is looking at the probability of waiting a certain amount of time for an event to occur. So I hope you enjoyed the lecture. Thanks for listening, and I will see you next time.